if the distance is bigger than the collision distance, but is lower than another threshold, then the following vehicle will have to decelerate. So it's deceleration area. Deceleration area. Okay. Now, if the delta x, if the distance is within this area, and if the difference of velocity is within this area, this white area represents an area that the driver is having unconscious reaction. Unconscious reaction. And that's why it's called psychophysical model. In the psychophysical model, within this region, the difference of velocity and the difference of distance cannot be detected by the driver. So the driver doesn't react to anything. This region. It's reacting in an unconscious way. But if in this area, for example, in this area, the vehicle ahead of me is traveling very fast, and our distance is big enough, then the vehicle ahead of me will leave me, and I will not react to it anymore. This is no reaction. This is unconscious reaction. But let's take a look at this. At this region, our delta x, our distance is already big, and the distance is decreasing. Our distance is decreasing. And then this vehicle has to accelerate to react. And probably you will enter this region, and you may enter this region to decelerate. See this? Within this area, the vehicle has to accelerate, because the vehicle ahead of this vehicle is having a noticeable distance, a small distance. So our distance is small, and my speed is less than the leading vehicle speed. So I'm going to accelerate. Are we clear? So this is acceleration or reaction, and you may enter this region to decelerate, or you may enter this unconscious reaction. So this is free driving, this is following, this is accelerating or also following, this is decelerating. Are we clear about this figure? If not, that's okay. In racing, we have two car following models to choose. The first one is called Wiedemann 74. It's based on his paper in 1974. Another one is Wiedemann 99. 99 is 1999 paper. The third one is called no interaction. In this model, actually in this option, using this option, we have no car following model. So it can be used for simplified pedestrian behavior, pedestrian simulation. The 74 model is suitable for urban traffic, like netting and crossing. The second one, the 99 model, is suitable for freeway traffic. In order to modify the parameters in racing, you have to go to base data and driving behaviors to open this dialog. After opening this dialog, you can choose the car following model from this drop box. Now you are looking at Wiedemann 74. It has only 3 parameters to choose. I want to mention one thing. This is a parameter called temporary lack of attention. Temporary lack of attention. This means the reaction time. By default, it's 0 seconds, which means the vehicles are reacting in an immediate way. So to reflect the reality in more accurately, you may want to choose this, to add this. And this is a dialog where you can choose the car following models. If you change the drop box to Wiedemann 99, you will see 9 parameters to choose. 9 parameters to choose. I want to talk about them. maybe very briefly, in the 74 model, we have the first concept to understand is called average standstill distance. This is the average distance between stopped cars. When we stopped, we have a distance. And this will have a fixed variation of 1 meter. 1 meter. So this is parameter we can change. If we change this parameter, we are going to see the Q gap varying. Now we have another measurement called safety distance. Safety distance is defined by the standstill distance plus another thing called Bx. And Bx is calculated by this thing, Bx underscore add plus Bx underscore multiply, and multiplied by z, multiplied by square of delta v. Suddenly I forgot what z means here, but delta v means the velocity. I think z value is link specific parameter, I guess. You can define these 3 parameters in the 74 model. Now let's take a look at 99 model, which is used for freeway. The first one is standstill distance, which is similar to the standstill distance in 74 model I introduced. It's the distance between stopped cars, but it has no variation in this time because it's used for describing freeway, so it doesn't have to be varied. The second one is called headway time. It's the time headway of 2 vehicles that a driver wants to keep. Time headway. So we say the safety distance is equal to that standstill distance plus headway time multiplied the travel time. This is CC1, the X safe. Now if we take a look at this table, this graph again, this line is defined by CC1 and CC0, this line, because it's the safety distance. All right? Now, following variation restricts how much more distance than a desired safety distance a driver allows before it intentionally moves closer to the car in front. It means this distance. If this distance, no, it means I think it means this distance and the top of this distance. Not very sure, but let's take a look at this definition again. So, how much more difference than the desired safety distance a driver allows before he intentionally moves closer to the car in front? I think it means both those 2 curves. Now, CC3 talks about how many seconds before reaching the safety distance the driver starts to decelerate. By default, I think it's 8 seconds. So 8 seconds before reaching the safety distance, the driver will start to decelerate. That's used in the approaching mode. And we have CC4 and CC5. That's to control the speed difference during the following state. In the following state, this is the following state, which the speed oscillates. This is approaching, this is following. So CC5 and the CC6 are complementary. Those 2 parameters are used for defining those 2 borders, these 2 borders. CC4 and CC5. One for negative speed difference, represented by percentage. The other one for positive speed differences. CC6, speed dependency on oscillation. This is going to define the speed oscillation with increasing distance. I also forgot what it really means now. Right, I'm very sorry about that. Now, C7 is the oscillation acceleration. This is the actual acceleration during the oscillation process. So within the car following, the white area, the vehicle starts to oscillate. This is the acceleration when the vehicle enters the following stage. Now, two more parameters. CC8, standstill acceleration. This is the desired acceleration. This has nothing to do with car following model, but it's a parameter that their model uses. It has nothing to do with car following. This is the desired acceleration when the vehicle starts moving, and it's limited by maximum deceleration. CC9, acceleration at 80 km/h. Very similar concept. Using these two parameters, we can get the acceleration at any time, any speed. But both of them are restricted by the maximum acceleration. So let's see how the maximum acceleration is defined. If you go to base data functions and maximum acceleration, you're going to see this dialog. In this dialog, you can, before entering this dialog, you can choose the car type. Then you can define the maximum acceleration for each car type. In each vehicle type, you are going to see three curves. The red dotted curve means the average maximum acceleration of vehicles. This is the minimum, this is the maximum. And you will see with the speed increasing, the maximum acceleration is also decreasing. Okay, I have finished talking about rhythm. Now I want to talk a little bit about parametrics. In parametrics, here's a table. I probably shouldn't show it very quickly, so quickly. In parametrics, the first thing you want to get and you're going to know is that it has a target headway. The target headway is the time headway between vehicles, and by default, it's 1 second. So the vehicles are keeping a 1 second time headway. They are trying to do that. But different vehicles or different scenarios are going to provide different variation factors. For